Welcome to the Cybersecurity Seminar Series put on through the UC-San-Francisco-Stanford Center of Excellence in Regulatory Science and Innovation and FDA. This speaker series is on cybersecurity for biomedical engineering. We meet every third Thursday through the academic year. And welcome back to the beginning of the 2022-2023 academic year. I have a few introductory remarks before I hand it over to my colleague, Bill Arts. So welcome back. You can see I have a new role. I am back at the University of Michigan as an associate professor, and I remain the series coordinator. And I'm also director of the Archimedes Center for Healthcare and Device Security at secure-medicine.org. Couple disclaimers before we get going. Just a reminder, this seminar series does not represent official FDA policy or guidance, and the contents are those of the speakers and do not necessarily represent the official views of, nor an endorsement by, FDA, HHS, or the US government. This seminar is being recorded. Couple of announcements. Looking for jobs, contact Diane Mitchell at fda.hhs.gov. Also an announcement that FDA is taking part in a Biomedical Engineering Society session on cybersecurity engineering education, how to introduce cybersecurity engineering into the degree granting curricula of universities. This is happening in person in San Antonio at the BMES annual conference on October 15th, where you'll find several representatives from FDA, as well as Dr. Christian Damoff and myself, to lead this session on how to move the field forward in training and education. Hope to see you there. It is my pleasure now to turn over the podium to our guest moderator, Bill Arts. So Bill, you can go ahead and unmute, and I'll let you go from here.
Thanks a lot, Kevin, and welcome everybody. It's really an honor to be part of this presentation today and to be working close with my good friend, Kevin Fu. Just by way of a little bit of introduction, I am currently the managing director and the senior fellow of the Center for Medical Device Cybersecurity at the University of Minnesota. Prior to that, Kevin mentioned that he's leading Archimedes. I was the executive director of Archimedes for quite some time, 4 or 5 years. And then prior to that, I served as a global director of product security at Medtronic, and then had other IT security jobs prior to that. So enough of an introduction. You can move on to the next slide. I wanted to just tell you a little bit about the center that I'm engaged with. First thing I want to say is that the strength of our group, the reason behind our group being in Minnesota, is that Minnesota has been a global center for medical device development and innovation. Started quite a number of years ago with the creation of the world's first pacemaker here I'm in Minnesota by Earl Bakken at the University Hospital. And Minnesota now continues to be a center of innovation in healthcare and technology with constant stream of research and literally hundreds of projects and startups across the area. It really is a hotbed for development of new medical device technologies in particular. That said, the Center for Medical Device Cybersecurity is a member-based organization that's continually expanding and active hub of connections and communications, education, training, resources, research, and useful experiences for all of those involved in improving security and safety of healthcare devices. If you're an organization that's looking for help or partnership or information about medical device security, we'd be a great group for you to be part of. Our members are healthcare providers and manufacturers, and we're open to sponsorships and other partnerships with other organizations. And you can see here is our website and our address. Please feel free to just send us an email. We'll make some contact and we'd love to talk to you more. Enough about that. As Kevin mentioned, I will be monitoring any questions or comments that you submit via the Q&A function. And if pertinent, I'll interrupt Kevin. Otherwise, we'll hold them off to the end. So as a way of setting up the topic, this is a pretty large issue and it's becoming more and more, particularly with healthcare, with device security. There's plenty of evidence that there are issues here, including this chat room run by a Russian group, cyber criminals that hit really during the point of the pandemic. In fact, healthcare is stressed even more because of the pandemic, of course, and so it makes these issues even more important. This was an article in the Wall Street Journal about a pretty significant event that happened during 2020. Next slide. There's quite a bit of activity going on in biomedical engineering. Cybersecurity for biomedical engineering include quite a few government things. This has been a little bit slow on the uptake, but now in the last few years, there's been a lot of activity. Both the FDA and Congress, there are a number of things that are going on, not the least of which was the executive order, the presidential executive order on nation cybersecurity, which has driven a lot of potential funding and planning around this issue of making healthcare secure. It's also worth noting that just on Monday, the FDA released an announcement to private industry saying that they've seen an incredible uptick in device healthcare security issues across the United States, and particularly with legacy devices, which is no surprise. Legacy devices have been an issue in this topic for quite some time. Next slide. So the FDA is certainly doing a lot. They are about to release a new updated version of cybersecurity medical devices, the pre-market considerations and integration with the quality. Kevin is going to talk to you about, you probably know Kevin just ended his time at the FDA and certainly was seminal in delivering a lot of the FDA's most recent activities. And there's, like we mentioned earlier, there's plenty of government activity with things going on in Congress and other things. Next slide. So it is indeed a pleasure. All of you know him, but it's really a pleasure to introduce my colleague, my friend, Professor Kevin Fu. His talk today on security engineering for medical products. He's associate professor of EECS at University of Michigan. He was the acting director of medical device cybersecurity at the FDA, the first role of that kind. And truly is one of the, I call him the grandfather of medical device security, as doing some work of 10 plus years ago on research on, in fact, discovered vulnerabilities in a pacemaker made by Medtronic when I was the security guy there. So we go back a long way. So without further ado, let me turn it over to my friend, Professor Kevin Fu.
All right, I think you can see my title slide here. So I'll begin. Thanks again, Bill, for the kind introduction and moderating today's session. Today is sort of a level-setting kickoff of the annual seminar series, and I'm going to be talking about a blend between medical device security and cutting-edge research on sensors and protecting the integrity primarily of sensors. So just a little bit about my background and disclosures. I did, as Bill mentioned, I recently completed my term as acting director of medical device security at the U.S. Food and Drug Administration. And I am back at the University of Michigan. Actually started getting my feet wet, or rather didn't get my feet wet because I had a wooden shoe, working in healthcare IT in the mid-1990s, deploying paperless medical record systems. But I should note today, all my opinions are my own and do not necessarily represent or reflect the views of any of my past or current employers. Here's my disclosure slide. I'm a director of Archimedes, consultant to the FDA. I did co-found Verta Labs, and Archimedes is supported through a corporate membership program. I do have recent support from the National Science Foundation and Analog Devices for the research you're going to see today. So let me try to paint a broad brush picture connecting medical device research to security research. So as Bill mentioned, well over 10 years ago, it was in 2008 that we published a paper, one of the first, actually the first paper, analyzing the security of a pacemaker that happened to be Bill's company at the time, and showing how to build in defenses. There's been huge advances on the technical side, as well as the public policy side, with huge strides being made in the cardiac community as well as the diabetes community, two communities that were early into the cybersecurity realm for medical devices. Now, at the same time, in the universities, we tend to focus on problems that are 5 or 10 years out in the world. These are not necessarily operational problems today, but we have a pretty good track record at predicting things 10 or 20 years ahead, such as the pacemaker security we did in 2008. So we're going to talk a little bit about this today, about how physics and computer security relate and how it also affects medical devices. So to level set again, before we get into computer security, I want to show you a clip from the New York Times that has to do not with security, but with reliability and interference. This is a video from New York where this homeowner is going to have his cell phone ring, and just watch what happens when his cell phone rings.
Let's see how it goes if we call your phone now. Well, oops. What is that beeping noise?
The beeping is like I press the button broil and then press the arrow to set on high.
Whenever this gentleman's phone would ring, his broiler would spontaneously ignite.
So even once you hang up the phone, of course, the oven stays on.
Yeah, and you'll see the flame coming in the oven.
So this was probably not part of the design spec, just as computer security problems are usually not part of the intended functions of a medical device. And so this was a case where there was no adversary. We never really figured out what was going on with this guy's oven. I suspect that the phone was emitting a radio frequency, probably at the resonant frequency of the piece of wire between the broil button and the tiny computer inside of the oven to control the gas line. And it likely misinterpreted a key press from that electromagnetic interference. Now, I would argue that correctness is easy, relatively speaking. I often ask my students how to define correctness for a keypad in order to enter a secure room. And they usually say something like, well, if you enter the security pin, the door should open. Now, defining security is much more complicated. It's also a negative property, and negative properties are hard to get right. So in this particular case, it was probably designed by committee, because as you can see, the committee put up a plastic placard with the numbers to enter the door, as well as if you can't read English numbers, they have the numbers in Spanish as well. And this is emblematic of classic security failure. You will find that adversaries usually don't go through the front door. They usually don't follow your specification. They create their own threat model. And the only real defense against a determined adversary is to be more creative than that adversary. Threat modeling we'll get into a little bit later, but it is just so key. And here's an example of when you do improper threat modeling in a parking lot. This meme has been circulating the internet for decades now. But it's still the best meme I've ever seen for threat modeling. As you can see, somebody designed a secure gate, and then they installed it in a system that had no security properties, as all the drivers were bypassing the gate by driving through the snowy, grassy field. This is typically how security fails, not being creative enough about a threat model. So we have many biomedical engineers on this call. We have many safety experts, and I'm going to challenge you to try to get out of the world of safety, where you have Gaussian distributions of failure, and try to move to the world of cybersecurity, where the adversary controls the probability distribution of unsafe conditions. And so if there is a 1% chance of something going wrong, the adversary will work to make that 1% happen 100% of the time. And so a lot of the tools that are used for safety begin to break down when you apply them to cybersecurity, because probability doesn't matter when it comes to computer security. The probability is always 1. So how are we going to engineer this out if the probability is always 1? Well, you're going to find we have to use different methods. Now, between the early 2000s and about 2012, pre-ransomware area, a lot was already going on with medical device security. FDA was investigated by GAO to figure out if it was regulating, how it was regulating medical devices. And malware was beginning to creep into hospitals, but not ransomware, just traditional malware breaking into hospitals. So in 2008, as Bill mentioned, I was part of a team that analyzed the security of pacemakers and defibrillators. One of the interesting outcomes was by building a homemade radio transmitter, we could manipulate the device. And I just want to highlight a few of the things so you can compare it to where we are today. I gave a defibrillator to my students and an oscilloscope, and they analyzed the radio communications between the implantable device and the bedside pacemaker defibrillator programmer. And they were actually able to decode all the radio communication because they could find no evidence of encryption. Everything was what we call in the clear. So essentially the entire electronic health record was readable by anyone who could build a radio receiver. Now that was a privacy issue, but we were also interested in the integrity and authenticity properties of computer security. So it turns out built into most defibrillators is what I would call a human debugging command. When the defibrillator is implanted in a patient, you need to make sure that the defibrillator has some kind of end-to-end check that it's going to defibrillate the patient when there is some kind of cardiac arrhythmia that can be treated. So built into the defibrillator is a debugging command, a wireless debugging command through RF that induces ventricular fibrillation. So my students were able to record the radio communication to disable all life-saving therapies. They recorded the communication to induce ventricular fibrillation, and then they replayed them, very much like a tape recorder, just replaying that communication, and it caused the device to emit a shock designed to induce a fatal heart rhythm and then not bring it back to normal sinus rhythm. This really led to where we are today, sort of a sea change in thinking, where it became clear that the community needed to get some kind of security engineering into the processes of medical device design. Now, medical devices are not alone. You will find, for instance, sensors and receivers everywhere. You'll find them in airplanes. You'll find them in autonomous vehicles. Airbags, in fact, are controlled by 2 or more accelerometers that trigger the detonation of the airbag. You also find these sensors inside cube satellites in orbit. Instead of reaction wheels, you can use some of these types of sensors to better understand how the satellite's inclination is and such in space. So putting my academic hat on and thinking about the future, this is not about a specific product. This is really about how we engineer systems today. My greatest concern is that we don't have a design pattern universally in place to prevent unintentional interference from violating and adulterating the output of sensors. And so I'm going to go through several cases where we used vibration, acoustics, radio waves, and even light waves to spoof sensors into delivering chosen messages to the microprocessor that can then change what the microprocessor does, how the adversary wants the device to behave. So the easiest example I can use for this is a thermocouple. And my admonition is that sensors are not really sensing what they tell you they're doing. They're actually a proxy for reality. And for instance, a thermocouple is advertised typically as, well, it senses temperature. But that's not what it does. A thermocouple interpolates from a voltage potential what it thinks the temperature is in a particular area by using some bimetals. It looks for the differential between 2 ends of the wire. There's a small millivolt signal that can be amplified and then interpreted by an embedded system. But it's not necessarily temperature. So my researcher, Sarah Rampazzi here, has a thermocouple, and you can also see she has a little toy antenna. And what's interesting is if you zoom into this thermocouple, you'll see the laboratory, my laboratory is negative 1,847 degrees Fahrenheit. A little bit chilly. I know we often complain about overzealous air conditioning in conferences, but this is sort of beyond the pale. In fact, this is negative 770 Kelvin, which makes no sense. It's below absolute zero. And so, first of all, whoever created this commercial embedded system clearly didn't have any kind of error handling routines for completely impossible temperature values. But it also raises the question, well, wait, what if an adversary is deliberately trying to emit radio waves in order to adulterate sensors that feed into some kind of closed loop feedback system? So where would you find thermocouples in closed loop feedback systems? Well, things like the vaccine cold chain, when distributing vaccines and making sure that those vaccines are kept at a precise cold temperature. Cryogenic chambers for embryos. You can imagine cycling coolant depending upon a thermocouple Imagine if you have a radio transmitter that can fool the system into saying, hey, I'm already cold, and then it stops the coolant from running. These are serious issues that we'll be facing in the next 10 years if we don't solve design patterns for security for sensors. The main problem is that how can we protect medical devices from these emerging threats, not to the digital systems where we have products we can buy today, but how can we protect against analog interference where there are no products today? Most of the commercial world focuses today on what I would call the system or the software stack, but there's this huge unprotected realm known as the sensor, the semiconductors that feed into the software, and it's effectively the analog equivalent to a buffer overflow. It's out of sight, out of mind, with no design patterns there in place. So the outline for the rest of the talk today, we're going to talk about how to defend against 3 different modalities of attacks on sensors. You will often find these kinds of sensors inside medical devices, again, as well as autonomous vehicles and even spacecraft. So what kind of medical devices depend on sensors? Pretty much all of them, right? Anything with a closed loop feedback system with some kind of automated therapy, or even a human in the loop system will use a sensor. So I want to talk about some early research we did on how to protect pacemakers from deliberate radio interference. And just to sort of wake you up this morning, I'll sort of challenge you to think about which one of these is the real cardiac signal. Is it A, the sinus rhythm on the left, or is it B, the flat line on the right? And while you're thinking about that, I'll just say it depends, right? So in the particular case I'm about to show you, if the patient had a flat line, we want to make sure we see that flat line and that we don't see a false signal of a false normal sinus rhythm. Because if you're a pacemaker, you'll be looking for the lack of a normal sinus rhythm and then deploy an electrical therapy to induce a heartbeat artificially. So if we were tricked into seeing the normal sinus rhythm, the pacemaker would likely choose to inhibit the pacing in a typical inhibiting mode for the pacemaker. So backing up again, there's a lot of technology out there you can just buy today for protecting network traffic and applying software updates. I would say a lot of this just has to do with a failure to deploy systems. The research on network security, I mean, the heydays were in the 1990s. A lot of that technology is well known how to do it, and it's really a matter of deploying and maintaining those kinds of systems. On the sensor side, you can't buy anything today. I am not aware of any products that can protect you against the kinds of things we're going to talk about today, but the good news is there's still time to build in security. So before we get to the pacemaker, I'd like to give you an example of using a microphone. So I'm speaking into a microphone right now. And between the microphone and the computer that's transmitting over Zoom, there is a piece of wire. That piece of wire has a length. And if you recall from high school physics, it therefore has a resonant frequency. It happens to be pertaining to a reciprocal of the speed of light, but you can figure out based upon the wavelength of radio transmissions, if your radio communication is at the resonant frequency of that piece of wire, you're going to get really high pickup of that signal before it goes into the circuitry, which typically is some kind of amplification circuitry, and then something that converts those analog voltages into bits that the computer and the software can understand. So for the circuit side, you'll often find medical devices and other systems defining what you call the baseband. So this is a plot, an illustration. You have frequency in hertz on the x-axis and then amplitude on the y-axis. You can imagine a pacemaker would like to see low frequency signals from cardiac tissue, because that's where most of the cardiac signals are, pretty low frequency, usually 10 to 100 hertz. So you'll likely want your sensors to just let all that all those signals in. Now, high frequency noise, you can build what's called a filter. These filters, they're circuits, they're doodads, little circuits. They filter out all the high frequency noise. It's pretty trivial to do, relatively speaking, but it's extremely hard to filter out signals that come in at the baseband. And so if an adversary is injecting signals at the desired specified range of signals that are meant to come into the device, the circuits aren't going to be able to help you at all, and you really need to solve this at the software level. So to demonstrate the implications of this in sort of a low consequence way, I'm going to show you how we do this with the microphone. So on the right, we have a software programmable radio, and it's an AM radio station. It's going to be sending out a signal from about 1 meter away. And you see we have a webcam where we've removed the plastic housing, and it has a USB cable connected to the Mac. We are recording the audio on the Mac in this completely silent room, and you'll see what the Mac thinks that it hears in the room because of the radio transmissions injecting information into the microphone circuitry. As you can see or hear, that was fairly clear audio. It sounds like walking through an airport listening to music. It is quite trivial to be able to inject these false audio sensations into microphones because of that length of wire. Why does this work? It's a little bit beyond, I think, the audience today, but if you're an electrical engineer or a ham radio enthusiast, you'll know that this is called self-demodulation as a result of nonlinearity and intermodulation distortion. At a very high level, it has to do with circuits are always imperfect. And there's a way to actually trick nonlinear circuits into becoming unintentional radio demodulators. It's similar to the apocryphal stories you hear about with somebody with braces able to pick up AM radio stations. There's an element of truth to that, and that's what we're doing here with the microphone and what we're about to do with the pacemaker, exploit the nonlinearity to be those braces to demodulate the malicious AM radio station. So how did we do this on a pacemaker? So pacemakers, of course, and I'm sure we have many pacemaker designers on the line, have leads. These leads do both sensing and actuation. They send shocks to the cardiac tissue for life-saving shocks. Now, within a single heartbeat, that you have the QRS complex, and that's a single heartbeat. And most of the frequency components of your cardiac rhythm is between about 10 and 100 hertz. And so, again, if the adversary is able to inject signals in that 10 to 100 hertz range, it will get through the filtering of the pacemaker and work its way up to the software stack and likely be misinterpreted as cardiac rhythms. So to test this, we used a very rudimentary ANSI PCI 69 standard of the salinity of human tissue with a highly calibrated refractometer of saline solution where we put the pacemaker in a saline bath. We also put a pacemaker on a wall and then used leftover copper tubing from my house to transmit AM radio waves across the room, and then to measure what kind of effects happen on that pacemaker. So if you just take a look at the left-hand side of this chart, you'll see we thought, well, if we emit a sine wave, so I didn't tell you there'd be trigonometry today, but there is. So we're emitting a sine wave today, and we thought, well, if we turn on this sine wave on and off every 1 second and just kind of pulse it, I wonder if that would be misinterpreted as a 60 beats per minute heart rate, cardiac rhythm. And sure enough, on this commercial programmer, you can see that the pacemaker was doing ventricular pacing because it was not attached to any cardiac tissue, and so it was sending out those regular pacing shocks. But then when we emitted the 3 pulsed sinusoids, you'll see it says VS, or ventricular sense. That means the pacemaker effectively said, hey, wait a minute, this patient is beating their heart normally. We don't need to send out a life-saving shock, so we're going to inhibit the pacing temporarily, and that's going to help with power saving, among other things. When we turn off the interference, the ventricular pacing resumes. And so this was a clear causal effect that our interference was taking control of that pacemaker and turning off the pacing ability while the interference was going. Now, that's the bad news. The good news is this doesn't work very well in practice because people are basically walking bags of saline solution. And at these particular frequencies, around 1 gigahertz, a lot of that energy just gets readily absorbed by human tissue in a harmless manner. So we could find that our attacks typically would not work beyond about 5 centimeters away from the device when it's inside saline solution. But it's a different story altogether for body-worn devices. Nobody's done the research yet on insulin pumps, but in cases where the sensors are outside of the body, you have less tissue to absorb that RF. Okay, so that was an example of radio waves and fooling sensors into delivering false, coherent information to an embedded system, such as a pacemaker. It's really the back door into the system rather than through the front door of the digital world. Now, I want to tell you about how you can do this with sound waves. It's not just RF. You can also do this with sound. So I'll play this video. We're playing an 11 kilohertz annoying tone you might hear. And there's a Fitbit inside this box. And this Fitbit step counter goes 81, 82, 83, 84, 85. Keeps increasing on the steps because inside the Fitbit is an accelerometer, a MEMS accelerometer. And it's missensing from our sound waves a false step. And so here's another case where using physics, an adversary can change the behavior of the device that was not intended. Now, to illustrate this a little bit further about what's going on before we get into the physics, this is a YouTube video. You can go watch this online if you go to my website or just search for Walnut. What I'm about to do is play a video on my Samsung smartphone. By the way, I don't recommend you play this if you have a Samsung smartphone because it's designed specifically for Samsung circuits. It is going to emit a tone from the speakerphone of that phone, and it's going to mechanically couple and vibrate the circuit board inside the smartphone. And on that circuit board is an accelerometer. We are going to vibrate that accelerometer at its resonant frequency, and we're further sending out tones that are AM modulating a desired output. And on this Macintosh, it is behaving as an oscilloscope. An oscilloscope is kind of like a patient monitor. It's just going to display a time series of the amplitude of signal coming out of the accelerometer. So one of the axes is going to show you the change in acceleration over time. And we're going to use it to spell out words on this monitor just to demonstrate the degree of precision that an adversary can control the output of an accelerometer just using sound waves. So here we go. So you can see that it's spelling out the word walnut. I asked my students to use all the capital English letters that are functions, not relations, and that happens to be W-A-L-N-U-T. And the other interesting thing you can gather from this demonstration is that sounds that are not near the resonant frequency of the semiconductor material are irrelevant. So you can actually lace these sounds into music videos and other things. And if it's played nearby the sensor, it will have this effect regardless of the background noise. It's also interesting, I won't talk too much about ultrasound today, but you can actually embed inaudible tones into videos. And so you can imagine playing a YouTube video with ultrasonic tones in it, and you, the human, won't notice it, but your sensor will have information injected to it. Why does this happen? What is going on? This is so bizarre. This all has to do with physics, because inside these tiny MEMS sensors, micro electrical mechanical systems that have been around for decades, are little cantilevers, nanometer-sized cantilevers, little ledges that shake. And basically, these devices convert how these things shake into electrical signals that are then interpolated into what kind of acceleration is going on. They're also used in modern devices for low power clocks. And so you're going to find these things all over the place, and they all are potentially vulnerable to acoustic injection, where the adversary can control or bias the output. So since we're a very blended audience, I'm not going to go too much into detail on the electrical engineering here. Suffice to say, we tested dozens of different kinds of accelerometers, and all had these kinds of effects, but they all have different resonant frequencies. And that's because they're made of different materials, and they all shake it in different ways. But what's interesting is, once you know what's, again, the resonant frequency, and in layman's terms, if you know about the opera singer who can shatter a wine glass by hitting a particular note, that is the resonant frequency. We're doing the same thing here, but instead of the opera singer, we're emitting a tone that is at the resonant frequency of the semiconductor material. And And it can lead to basically two interesting electrical conditions. You'll get a weird fluctuating output from the sensor, or you can get a constant value coming out. Both of these things under the control of the adversary. The reason for this gets into some pretty deep electronics. So this is probably speaking to maybe 5% of the audience at the moment, but all sensors are composed of these 5 stages inside the circuit. And there's 2 very interesting stages. One's called the amplifier. This is where you take a small signal and make it really big, because computers tend not to work very well on tiny signals. And then there's something called a low-pass filter. This is a way to get rid of all the high-frequency noise that you don't want going into your software. And it just turns out that because of certain design choices in amplifiers, has to do with something called asymmetric clipping, and low-pass filters that tended to not actually filter out so well, the adversary is able to control the output of the sensor.
Kevin?
Yes, question.
Let me just step in here. There's one that may be relevant here. One question is, are these all examples of side channel attacks, or are they classified as something else?
Okay, so the question is, are these side channels attacks? Technically, I would say these are not side channels. So the side channels community, you've probably heard of Rowhammer, Spectre, and Meltdown. These, at least Spectre and Meltdown, those are classic side channel attacks where you're reading information out. And if you ask what property are you violating of security, security is not a property, but security has properties. And those properties are either confidentiality, integrity, or availability, or a few other ones. Traditional side channels research violates confidentiality. They're able to exfiltrate information. We're doing the opposite here. We're closer to Rowhammer. We are using signals to damage the integrity and adulterate the information rather than violating confidentiality. So we don't usually call it a side channel. We usually call it signal injection or a transduction attack, but it's sort of the opposite of a side channel. You can think of it as a write side channel as opposed to a read side channel. Thanks for the question. That's a good one. So the defenses for this are really interesting, because I know many medical device manufacturers get reports from Department of Homeland Security where it usually reads, hey, there's this popular software package. It's embedded in a lot of medical devices. Please apply a software patch. And that's usually the solution. In this case, DHS and the manufacturer released a document that said, hey, everybody, you should drill your holes differently on your circuit boards. And that is the fix. So it turns out there are multiple ways to get sound waves into sensors. And one of the common ways is board deflection. If you think about it, when you put a circuit board in your medical device and you have mounting points, you just created a drum. So you didn't know you're a musician, but you're a musician. And when those sound pressure waves hit the circuit board, it starts to deflect and adds a secondary acceleration. And this adds artificial acceleration to the sensor. So the security advice was to drill the holes much closer to the sensor to make it more rigid. And this drives the resonant frequency up into the ultrasonic ranges, which are traditionally more difficult for an adversary to achieve because there are fewer readily available ultrasonic transmitters. And they also recommended, and this is key, trenching. This is not only going to help with safety of unintentional interference, but it's also going to help with security. You want to physically separate and mechanically decouple your emitters from your sensors. So in this case, if the smartphone had cut a hole between the speakerphone and the accelerometer, it would have been very difficult to get good mechanical coupling to transmit that undesired malicious signal into the sensor. And so those are the approaches that, in this case, Analog Devices, which now funds my lab, is advising in order to reduce the risks. It doesn't get rid of all the risks, but it does help significantly drive the risk down. But I was just amused. It was one of the first time I saw omega T and sine waves in a DHS CERT report, but there it is. I'm going to skip a couple of the super technical slides here, other than to say we do have a couple software approaches where you don't have to actually go off and buy new hardware or resolder your circuit boards of pacemakers and people. But you can actually apply a software update to the firmware in order to reduce the risks of a lot of these particular kinds of attacks. So we have about 15 more minutes. So I want to make sure I get through the next section here. We've talked about radio waves. We've talked about sound waves. Now I'm going to talk about lights. And this is probably the most unusual one I've worked on. Here we have a photograph. This is not an illustration. We actually got permission to go into a bell tower and shoot a laser into a faculty member's office through a plate glass window to hit his Google Home, and precisely hitting a microphone on the top of that Google Home. And we're going to be shining this laser pointer on and off very quickly to trick the device into hearing false voices. So this is some research called light commands. You may have seen it on NBC Nightly News with Lester Holt. And we're going to go through now what's going on with some of the physics. So just to give you an idea of the setup we have here, we've actually taped Google Home, not on that white wall in the back, but the brick wall, several hundred feet in the background. And we bought a used telescope and then sort of retrofit it. We jerry-rigged a collimator. So you might know collimators from radiation therapy devices where you try to collimate the ionizing radiation. Here, we stuck a laser, a diode-based laser on the back of a telescope to use it as a collimator to do beam forming. And we're going to make sure that we have a crisp laser point many hundred feet away. We are sending in a signal. The signal happens to say, hey, okay, Google, open the garage door. And we've modulated that using AM, just like AM radio, amplitude modulation, on top of a carrier frequency that happens to be where things resonate. So I'm going to show you a short video about the consequences of how this works, and then I can take questions about how it works in just a moment.
Okay, opening.
So that was an example of the implications of voice-controlled systems. And this also cuts to the problem of threat modeling. And you'll hear this from the medical device security community all the time. Step one is threat modeling. Voice-controlled assistants used the threat model of, hey, if you're not in the room near the microphone, you can't put sound into the microphone. Turns out this violates that threat model, and it's not a very good one. So here we have a short video explaining why it's important to use a threat model where an adversary from a long distance can beam sound into voice-controlled assistants.
In May 2019, researchers from Japan and the University of Michigan discovered light commands, a vulnerability in most microphones that allow attackers to remotely inject commands into voice assistants such as Google Assistant, Alexa, and Siri. So, how do light commands work, and how can we defend against them? Voice assistants operate on commands spoken by the user, such as, Alexa, what's the weather? Or, okay Google, unlock the front door. While the security of voice assistants is a common concern, assistant-enabled devices are typically kept indoors, where access is restricted to only legitimate users. So why are light commands so dangerous? To understand light commands, let's take a look at how microphones work. Microphones convert sound into electrical signals. Inside each microphone, there is a small plate called the diaphragm. When sound hits the diaphragm, it moves, resulting in electrical signals. An attacker may try to move the diaphragm by yelling from outside. However, as solid objects block sound, the command will probably be ignored, as well as noticed by nearby neighbors. Light commands, on the other hand, exploit different tactics. Instead of sound, an attacker can encode commands via the intensity of a laser light beam. By shining a laser light through the window at the microphone, an attacker can remotely cause the diaphragm to move. This results in electrical signals representing the attacker's commands, which are then acted upon by Alexa, Google Assistant, or Siri. Making things worse, light commands can be mounted easily and cheaply, even using regular laser pointers. This can even be done from far away, for example between two buildings. Even more worrying, once an attacker has gained control over a voice assistant inside a phone, tablet, or smart speaker, they can use it to break other systems. For example, the attacker can control smart home switches, make online purchases, open smart garage doors, remotely unlock and start certain vehicles, or open smart locks by brute forcing the user's PIN number. So how can we defend against light commands? While the basic vulnerability cannot be addressed without expensive microphone redesign, we are collaborating with Amazon, Google, Apple, as well as other vendors on defensive measures. If you would like to know more, check us out at lightcommands.com.
All right, so I hope that gave you a sense of sort of what's coming in the next 5 to 10 years. The adversary is usually one step ahead. And in this case, we're trying to build in defenses. And so we have a whole set of lectures, actually, I teach at the university on how to build in things by design to prevent these kinds of issues. The take-home message, if you're building a medical device and you depend on sensors, keep using those sensors, but you need a way to verify the trustworthiness. And so in the university system, we're trying to now move away from compliance-centric thinking, checking off forms like, do you have a firewall? Those kinds of things are kind of high school. And so what you really need to do is test a security failure. And so in the university, we teach students how to unwrap all these digital abstractions so they understand how do they fail and when do they fail. And we have them explore the undefined behavior of circuits and software in all those places where you're not supposed to be working, below the voltage levels. It's also really important, in my view, to begin to move away from sort of ad hoc security of just buying things and to have something be measurable. And to be measurable, it needs to be able to be not just a yes or no answer of did you buy it or not, but it needs to have a notion of shades of gray. There needs to be a notion of risk. It needs to have a limit at which it will fail. If it doesn't ever fail, I don't believe it, because the question is always going to be how powerful of an adversary does the adversary need to be for the design to fail? And then you design to your threat model of the particular strength of adversary. Thinking longer term, and this is, again, what we do in the university system. If you think about how Silicon Valley came to be or how integrated circuits were born, it was invented by engineers, right? And so one thing that I think we need to do is change the way sensors are manufactured. And we need to build into these sensors hardware software APIs such that the hardware can expose hints of trustworthiness to the software stack. So instead of, for instance, giving me a temperature value with a millivolt peak to peak voltage, we should also be saying, well, have I resonated at my resonant frequency recently? To give a hint to the software stack on whether you should trust in the veracity of that sensor measurement. We need to get away from simply trusting that because it's wired in, that it's for some reason an honest measurement. Now, these risks have been around us forever. The only change is that we're ceding control to computers and they're becoming much more ubiquitous. So maybe it's just not a good idea to put a sensor computer in everything unless there's a good risk-related reason. There's tons of embedded security research papers you can read in this space. This is just sort of a sampling. You'll find this in the YouTube recording, so I won't go through them all here. But I would just say the big vision here is how do we get toward trustworthy computing? How do we get to a world where science-based security is built in by design to all embedded systems, not just medical devices, but also healthcare delivery in general, autonomous vehicles, factory floors, which again are sort of the back door to a lot of systems, including medical device and pharmaceutical manufacturing. And don't forget the Internet of Things. The Internet of Things, to me, is simply putting transmitters everywhere. And so now that you have LED light bulbs with microchips with firmware, now an adversary who can compromise a light bulb can put one of these RF transmitters right over your head, and there's no longer a distance argument. It's extremely important now for the university systems and industry to work together so that consumers can get the confidence into security and privacy, because we can make the most innovative medical technologies in the world, but if consumers are scared away or don't trust these systems, they're not going to be effectively deployed. So it's extremely important that we're able to get these design patterns for defenses into systems today, not only into the education, but into the product manufacturing. So I'll just conclude with that microprocessors should not blindly trust what sensors are telling them, even if it's with a wire, because those wires can be compromised. Those sensors can be compromised with radio waves, with sound waves, even light waves. The defensive approaches, I didn't get a chance to talk about too much in this talk, but there are software approaches that can actually leverage physics to make it much harder for the adversary to succeed. And the key engineering approach here is get away from the world of secure components. TPMs, firewalls, they have a role, but they're not going to be your end-all solution. You need to make sure that your system remains trustworthy, even if you're using untrustworthy components that can be compromised. And that is what we call a trustworthy system. So I think I'll end here, turn it back to Bill. We have maybe about 5 minutes for questions. And again, welcome to the kickoff of the CERSI seminar series on cybersecurity for biomedical engineering. And Bill, I'll hand it over to you now.
Kevin, thanks. Very great, interesting stuff. Like a whole nother avenue of concern for medical devices and technology in general. One or two questions. First, this goes back to your original mention of threat modeling, and you've peppered that theme across the presentation. But one question is, are there any standards or guidelines to use as a reference for threat modeling testing for AI or machine learning enabled medical devices?
That's a good question. So there's FDA guidance, and then there's standards groups guidance, and you're going to see a blend of different things coming up. I would say at this point in time, you can find on FDA's website quite publicly just sort of generic threat modeling of systems. Now, when talking about AI and machine learning, I have an entire lecture on how to fool machine learning systems at the sensor level here and defensive approaches. I would say it's so early. There could be some guidance out there in the future, I think, but the science is still being done. In some sense, the industry has come to love machine learning so much, they deployed it before we figured everything out from the basic fundamentals of the science. So you may have heard of things such as machine learning basically is statistics combined with stereotyping. And so just like humans can make mistakes by stereotyping, so does machine learning. So we have a research paper, for instance, where it turns out that camera lenses have something called optical image stabilization to de-blur images. You'll find it on the back of most smartphone cameras. That's why you get a crisp picture. And you can use a machine learning system to automatically identify objects in the video. Well, it turns out that machine learning takes little shortcuts. They might think that, oh, this color represents a stop sign, or, this general triangle, oh, it's probably a human. Well, it turns out if you send out certain sound waves, you can shake the lens at its resonant frequency and create blur patterns that are effectively blurred silhouettes, and those silhouettes are misinterpreted by the machine learning layer as the objects the adversary is trying to falsely inject into the system. No standard is going to be able to protect against that right now. I would say in the absence of these standards, you fall back to good engineering practices. So the security community, the trustworthy systems community has an entire curricula and books on how to design systems to remain secure, even when, for instance, the machine learning layer is not completely trustworthy. I think it's really important to have standards communities thinking about this, but it's not going to be easy because they need to work hand in hand with the university systems where it's still a lot of the basic science is being worked out. So I think it's going to be challenging. I think we can have some high-level guidance. There's certain sort of easy things, such as realizing that shortcuts exist in machine learning means that you need to have the machine learning into your risk management for security, right? Maybe it's an acceptable risk, maybe it's an unacceptable risk. Maybe you'll have some compensating controls in place, such as alerting a human when something unusual is happening, such as maybe you're moving at your resonant frequency. But this is going to be a long journey on the machine learning side, on the sensors for sure. And I would say most of the advancements happening right now are in what I would call classic machine learning on just pure data.
Very good. Another question. How do you suggest small hospitals with limited resources start building out medical device security programs? That's a loaded question that I certainly have some thoughts on, but I'll let you answer first.
All right, thanks for the question, Will. It is hard. So there are some small healthcare systems that don't even have an in-house IT department. Sometimes they will outsource this. If you're outsourcing, I think it's really important for those outsourcing communities, and I don't need to name them here, but we all know the major outsourcers, it's extremely important for them to work on the system engineering and the integration piece, because a lot of the problems really come up with integration piece and making sure you have a plan in place for patching and updating. Patching and updating from an academic perspective is not the right approach, because you can actually design a system to be secure for quite a long time by designing things well. But humans make mistakes, so it's extremely important for systems to be patchable. I would say probably the area that would reduce the most risk would making sure that medical devices can be patched and updated in a very timely manner. How to do that? It is challenging, but I'll tell you what, the best way to be able to have things be patchable, how do you lose less, have less? So simplifying systems, of course, that's easier said than done. It's also really important to have a good track, in my view, of your inventory, because you can't protect what you don't know you have. There's a whole litany on things that can be done. I can also tell you that a lot of small health systems are often thinking about mergers and acquisitions with larger healthcare systems. And I can tell you that during acquisitions, some of the small healthcare systems were devalued by the purchaser because of poor cybersecurity hygiene. It was considered a major cost of having to do the acquisition. So putting effort into cybersecurity and budgeting for cybersecurity is going to be important. Of course, a small hospital, yes, it's going to be challenging because unfortunately, attackers don't give you a get out of jail free card just because you're a small hospital. The attackers are going to go for the low-hanging fruit, whoever has the least protection.
I would add just two little adds onto that. I agree with everything you said, Kevin. One is that I would say look for other groups, not meant to be an over promotion comment about the Center for Cybersecurity at Minnesota or even at Michigan, the programs there, but they can be very helpful in making connections. The other thing I would say is look to the healthcare, the Health Sector Coordinating Council. Do a Google search on that. They have some great action plans that you can use as a guide to start developing your program that are really best practice. One more question. Something that is happening now is AI designed circuits. Would this be an interesting direction for security?
AI designed circuits. So that is an AI making a circuit. I would say that's a playground for hackers because AI and machine learning is, from my sort of perspective, it's basically stereotyping. You draw a line at classification and you're going to stereotype all this kind of classification of objects or whatnot. That's going to be a hacker's dream. They're going to love playing with that. So yeah, you can do it, but just realize that you're going to be a really juicy target. And there are hundreds and thousands of really smart people out there. If you're going to choose to do that, you better have a vulnerability disclosure plan. You better have a coordinated disclosure plan. You better have right up on the front page of your website, how can a security researcher contact you if they discover a problem? Because I've seen too many times where a security researcher tries to get in contact with the manufacturer. The ones who have sort of with open arms accepting vulnerability information tend to do really well. The ones who make it really hard to find, or worse, the ones that sort of send the lawyers after the researchers, it usually doesn't pan out well for the manufacturers. So if you're going to do something pretty far out, like AI designed circuits, just realize it's going to be a fun playground for the hacker community.
And with that, I think our time is up. Thank you for the pleasure of being your moderator. Kevin, you can have the closing comments.
Well, thank you for coming and hope to see you back every third Thursday. We'll be having a blend of different speakers as well as panels this year that we'll be announcing shortly. So make sure to stay up to date on our website. And you can always reach out to me, Twitter at Dr. Kevin Fu, or you can find me on one of the websites up here and I can make sure that you're on the announcements list.